We're going to spend a couple minutes now looking at three special terminations, and they're special because they are often utilized in communication systems for their unique properties. And these three special terminations are the matched line, in which the characteristic impedance of the transmission line and the impedance of the load are the same. So in this case, I'm showing that Z0 is 75 ohms and the load is also 75 ohms. The second condition is the open circuit, which is there is no connection between the terminals of the transmission line. So we've got whatever Z0 is. It doesn't have to be 75 ohms. It's just Z0. And then it's just open circuited. In this case, I'm indicating that an open circuit can, in simulation softwares and things like that, can be simulated as 999 mega ohms. It's just a really large resistance, right? It's very difficult for current to flow from here to here because it's an open circuit, i.e. a large resistance. The third situation that we'd like to look at is the short circuit. So a short circuit is when a wire is connected directly between the output end of the transmission line, and so we'll approximate that in circuit simulators and such things as 1 microohm, an extremely small resistance. Current can flow very easily, and just like in the open circuit condition, in the short circuit condition, this can be any Z0. So the matched condition just means ZL is equal to Z0. ZL equals Z0. So those are the three conditions that we're going to look at in a little bit more detail now. Let's begin looking at these special conditions by analyzing a matched line on a matched load on a lossless T line. So we've got some sort of voltage source. It's got its internal impedance associated with it, and we then connect that voltage source with its internal impedance with a transmission line to a load, ZL. Z0. This is the Z source, and this is the V source. So this is the circuit we're going to talk about. And for a lossless T-line, you'll remember that Z0 is equal to the square root of L prime over C prime, and that's because R prime and G prime both equal 0 for the lossless case. So that simplifies our equation for characteristic impedance of the transmission line. You'll also know that L prime divided by C prime, that's going to be henries per meter divided by farads per meter, and that's ohms. And it's a real number, despite the fact that this is a reactance and this is a reactance. The characteristic impedance is going to be real valued. It's going to be a resistance only. So for a matched condition to occur on a lossless transmission line, Z0 is purely real, and it has to equal ZL, which also has to be purely real. So for a lossless T-line, for it to be matched, all of this reduces down to R0 is equal to RL. If we were to calculate the reflection coefficient at the load, right here, the reflection coefficient that occurs there, we have reflection coefficient is equal to Z0 minus ZL over Z0 plus ZL. And so in this case, we've got R0 minus R0 over R0 plus R0, and that's equal to 0 over 2R0, or just 0. So we've got a reflection coefficient of 0. We can calculate the VSWR from the formula 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient. And so that's 1 plus 0 over 1 minus 0. So that gives us 1 over 1 is just 1. And what this shows us is that for a matched transmission line and load, under the lossless assumption, there's no reflected wave, and the voltage, the VSWR is 1, meaning that the voltage is flat along the transmission line. So if we were to plot the magnitude of the voltage along the transmission line, for this case, what we would see is that at the load, the magnitude of the voltage is going to be V bar plus. Since there's no reflection, all we have is whatever the magnitude of the incident wave was, and since there's no reflection and the voltage standing wave is 1, the magnitude of the voltage along the length of the transmission line is constant at the magnitude of V bar plus. We can also calculate the input impedance of this matched lossless line at any distance d, and that calculation is Z in is going to be of whatever the length of line is going to be equal to Z0 times ZL plus J Z tan of beta L. So you notice that I'm using the lossless formulation of the input impedance equation. So that's over Z0 plus J ZL tan beta L. And so what I need to do is plug in R for all of these, and we get R times R plus J R tan beta L over R plus JR tan beta L. So the numerator and denominator are the same, so that is equal to R. So Zn of L is equal to R. So the input impedance, what that tells us is that for any length L, the input impedance of a matched lossless line is just R. So I'll say it again, the input impedance of a lossless line terminated in its characteristic impedance is constantly valued at all points along the T line and is Z0. So if I were to plot the magnitude of the input impedance, or if I would plot the input impedance as a function of distance along the transmission line, it's also constant at the value of R0. Since there's not a reflected wave, the only voltage along the T-line is the traveling wave. Therefore, the peak magnitude of the voltage measured at any given point along the transmission line is the same. The same is also true of the current. If I were to plot current on this instead, the current is constantly valued at whatever the I bar plus is, right? It doesn't change as a function of distance along the transmission line. This is a pretty important finding because what we see is that the input impedance of the transmission line that's terminated in a matched load is constant along the length of the T-line and is equal to the characteristic impedance of the T-line. So it doesn't matter how long the transmission line is, it's got a constant impedance associated with it.